Okay, hello, welcome to my channel. My name is Scalar, and in this video we're going to deal with some examples on dot products of two vectors. Good. Okay, so we have the following. We have to find all vectors perpendicular to this given vector containing 5 and -7. Okay, so in the previous videos, one of them, we dealt with some properties of dot product of two vectors, and it will be important to remember this one, that we have when we have the dot product of two vectors. Let's say the two vectors are a and b, where the angle, that is the angle between their directions, is 90 degrees, that's pi over 2. If that's the case, then we noted that the dot product of two vectors will just be the product of their measures, that is the product of their magnitude, times the cosine of the angle between them. But in this case, we say the angle should be 90 degrees. That's what it means for the vectors to be perpendicular. But then what is cosine of 90? Of course, that's just simply 0. So we get everything here to be 0. Okay, so this tells us that whatever vector we will find, okay, that if we dot it with this vector, we'll just get 0 as a result. So let's assume to be the vector to be v, and is given by v1, v2. Good. That is to say, we are going to take the dot product of v with this given vector. So I'll just take 5, -7. Okay, I dot that with v, which contains v1, v2. Okay, great. And then since we need vectors that will be perpendicular to that, we just have to set that dot product to 0. That's what it means for a vector to be perpendicular to another. All right. Okay. In a previous video, we dealt with expansion of vectors using expansion of vectors in Cartesian coordinates. So we're just going to apply that right here, and we learned that we have to multiply the corresponding entries together. So we say 5 times v1, that's just 5v1, right? And then we add that with negative v2, that's -7v2. Okay, great. Then we equate that to 0 because the dot product will just give us a scalar. Okay, so we can simply see here, maybe let's just move this to the right. That will become 7v2. Okay, and then we could easily divide both sides by 5. That means v1 would be 7 over 5 v2. Okay, so this tells us that whatever vector we want to be in this form, the first entry should be 7/5 of the second entry. Okay, great. So the first vector, that is v1, since it is 7/5 of v2, we just replace that. Okay, so whenever a vector has this form, okay, we are assured that such a vector will be perpendicular to this vector given. So how do you see? Well, let's think about v2 as 1. If v2 is 1, then you know that the vector we will consider will now be 7 over 5, 1, right? If v2 here is 1. So if we dot this with this vector, easily observe that 7 over 5 times 5 is 7, then 1 times -7 is just -7, and if you add those together, you get 0. Okay, so this is indeed for a vector. You know that it's not just one vector, there are infinitely many vectors, okay, as many as the numbers are. Good. Okay, so let's get right to the second example. Okay, so for the second one, we want to find, okay, so for the second example, we want to find a real number lambda such that this vector is perpendicular to that vector. All right, so we're just going to use the same property. So for two vectors to be perpendicular to each other means that their dot products will give us 0. All right, so I'll take 2i plus 3j. All right, that's 3 times the unit vector j. So this is a little different notation. I've dotted that with 6i plus lambda j. Okay, great. But since these two vectors are perpendicular, we want to find alpha that will make that true. Okay, so we just equate the dot product to 0, just like we observed from the first example. Okay, the next thing will be to multiply corresponding entries. 2 times 6 is just 12. Then when we say I dot I, that gives us 1, right? From the properties of dot product, that if we have a vector dotted with itself, okay, we should just get the vector dotted with itself. Usually it gives us the square of the magnitude of that vector, but since this right here is just a unit vector, it means we're just going to get 1 square, which is 1. All right, great. Then similarly, 3 times lambda will give us 3 lambda, but then j dot j is 1, so we equate that to 0. Okay, we could easily see here that lambda would just be -4, right? Okay, great. So that was so easy, just by using the property. Okay, so you could easily replace this with -4. All right, great. Let's do the third example. We want to find all vectors orthogonal to this vector containing entries 1, 1, 0. So you could say, okay, so what's orthogonal? Well, this is just a generalized form of perpendicular. So if you have vectors in R2, you could easily say those vectors are perpendicular. But in R3 or higher dimension, we use orthogonal, so it's a more general term which would include planes as well. All right, great. So find all vectors orthogonal to a vector given by 1, 1, 0. Actually, it's not really necessary to visualize this because the entry in the z-plane is 0, which means we'll just exist in the xy plane. But maybe let's just see what we can get. So let's say this is the z-axis, okay, and then this is the y-axis, and then the x-axis. All right, great. So let's think about, since those are the principal axes, let's think about vectors I, the unit vector I, j, and k to be along those principal axes. So this is for y, and this is for x. So this is 1 right here. So on the x-axis, we could get 1 somewhere there. On the y-axis, we could get 1 somewhere here, such that the vector we are thinking about, the position vector will be from, sorry, let me use a line for that. Position vector will be somewhere here, right? So you could get that. Okay, so that's the vector we are interested in. And then the z entry is 0. That means it lies entirely on the xy plane. All right. So we want to find all vectors orthogonal to this vector. So you could think about something like this. Maybe you could have a vector pointing in that direction such that the angle between these two vectors is 90 degrees. That's what we mean to be orthogonal. Or you could also have maybe a different kind of vector. Maybe it could go this way. It could go this way, regardless, provided that the angle between them is 90 degrees. Okay, so we'll just use the same approach we used for the first example, just that this is in R3. So what we just have to do is to assume the vector to be, maybe let's think about the vector as W. All right, it has those entries. So when we take the dot product, we say 1, 1, 0, dotted with a vector containing W1, W2, W3. What we'll just get will be, okay, and we need this to be equal to 0 because we said orthogonal, right? So what we'll just get will be, so that means we'll get W1, that's 1 times W1, plus W2, that's 2 times W2, plus 0 times W3 is W3, we equate that to 0. That means W3 is a free vector, it's a free entry, rather, it's free. That is to say, our result is independent on the value of the entry in the z-axis. So whatever W1 and W2 are, the z entry can be any value, right? That's what it means. So it's free. So from here we could easily see that W1 has to be negative of W2. So maybe let's rewrite the vector W, which will be maybe a set or an entry, sorry, which will be an element of a set, all right, containing all vectors orthogonal to our given vector. So this should be W1 is negative of whatever the second entry is, then the second entry, and then the third entry, which we said is free. Okay, great. Actually, the second entry is also free, but the first entry has to be the negative of whatever the second entry is. Okay, so using this our diagram, maybe let's draw another one. So using this, let's see what's going on here. All right, just a little bit. Okay, so let's say those are principal axes. Then what happens is that the given vector was something like this. The given vector, let me use a line for that, was something like that, all right, which was 1 to the in the x along the x-axis and 1 along the y-axis. Now, from what we've been given, we know that whatever W2 is, let's say W2 is like let's say something like 2, all right? So that will be negative 2 along the x-axis. So you need a line that goes that way. Okay, then we say negative 2 along that axis. So you see you need negative, that is the extension of the x-axis, but that is towards the negative part of it, right? So you need something like that. Maybe this is negative 2 along the x-axis, so I'm going to the other side. Then 2 along the y-axis, so maybe let's say 2 somewhere here. And then whatever z wants to be. So if you assume z to be 0, it means you will get a vector line entirely or line exactly in the xy plane, right? And this vector is assured to be perpendicular to the original. Or you could think about z as some value on its axis, so you could raise that vector up, so it could have some unit above the xy plane, but again it is still orthogonal to the original vector. So let me just use a different ink to show that it could still be orthogonal to the original vector. It could be infinitely many of them. That's why the question says if you find all vectors orthogonal to that. So you could assume w to be anything, right? But this is the structure we are expected to have. Now over to the last example. So given these 3 points A, B, and C, we want to find all interior angles of triangle ABC. Alright, so it's important that we visualize these points. So you notice that each of the points has 2 entries. That is to say, we are in R2. Okay, so let me get a line. Alright, so we let's say we have, this is the y-axis. Alright, maybe let me make it longer than that. Oh, sorry. This right here is the y-axis. And then that right there is the x-axis. Right? Okay, great. So let's call this 1 on the y-axis. Maybe let's call that 2, 3. Maybe let's call this 5, because I noticed that we will need 5 at some point. We need 4 as well. Okay, this is 1. I don't need to make it look dirty. Let's just forget about the numbers. Okay, so this is 4. Okay, all right, so notice that the first point, point A, needs 1 on the x-axis and 1 on the y-axis, so we could get that for the point A. Then the next point, point B, needs 3 on the x-axis and then 5 on the y-axis, so we could get that for point B. Maybe let's write that down. Point B, this is point A. Then lastly, point C needs negative 1 on the x-axis and then positive 4 on the y-axis, so that could be point C. So maybe let's join these points with straight lines. Then we'll get a triangle. All right. Okay. That is really nice. Okay. Great. So we need the interior angle. So it will be important if this is point C actually. So let's call this angle theta. Let's call this angle alpha. Then let's call this angle beta. Right. So you notice that angle alpha, okay, that is alpha is an angle between vector from A to C and a vector from A to B. So maybe let me just put that down, that the angle between these two vectors, a vector from A to C and a vector from A to B, is simply alpha. Then the angle between this vector from B to A and vector from B to C, that is vector whose initial point is B and the terminal point is A, and another vector whose initial point is B and terminal point is C, is simply beta. And then lastly, another angle, angle theta, is the angle between CA and then CB. All right, so that's angle theta. All right, so that's what this means. Okay, so let's think. We want to find all the interior angles of this triangle. Okay, so if you're thinking about alpha, what value should it have, right? Given that it lies between vector A to C and then a vector from A to B. Well, I recall one of the properties of dot products. Okay, of course, we are dealing on examples of that. That if you have two vectors, all right, inclined, whose directions incline at an angle, at any angle, so in this case the angle here is alpha, then we could easily use the definition of dot products. So for angle alpha, okay, what do? We easily recall that cosine of angle alpha would simply be the dot product of the vectors Okay, let me just remind you in case you've forgotten a little bit. Oh, what's that? Okay, so let me just remind you in case you've forgotten a little bit. So let's say this is vector A, then this is vector B, such that they are inclined at an angle. Okay. Maybe let's call that angle, I don't want to use theta, let's call that angle gamma. Then the cosine of gamma is simply, if this is A, and then this is B, okay, cosine of gamma is simply A dot B divided by the product of their lengths, AB. Alright, so using that, we simply have this to be the product of these two vectors, AC dot a vector from A to B, right, divided by their lengths. So for me to just say line AC times the product of their lengths times line AB. Okay, similarly, we'll get a cosine of the next angle there is beta to be, similarly, we say BA BC, right? So we say BA times BC divided by their lengths. So I'll just say line BA times line BC. Okay, and then lastly, you're going to have for, that is cosine of theta to be, well, in this case we just say CACB, so CA vector pointing from C to A dot vector from C to B divided by their length, so that's line CA and then times line CB. Okay, that's nice. What's going on? Okay, but what is vector AC? Well, vector from A to C, that simply means a vector whose terminal point is C and then whose initial point is A. To find such a vector, we just have to say the terminal point minus the initial point. So for this vector C, the terminal point is at -1, 4. So the vector will be this way. To be a vector containing these entries. So let me do that. So you have -1, okay, that is, recall the video where we dealt with how to find a vector using its endpoints, right? So we could say the terminal point minus the initial point. So in this case it would be -1 minus 1, which will give us -2, and then 4 minus 1, which will just give us 3. So that is vector from A to C. Then we dot that with vector from A to B would be B minus A. So you say 3 minus 1 is 2, and then 5 minus 1 is 4. Good. And then we divide that by, well, this is the product of their lengths, which will simply be the square root of 2 squared plus 3 squared, that is square root of 13, right? Then times the square root of 2 squared plus 4 squared, that will be square root of 20 if I'm not mistaken. 4 squared is 16, then 2 squared is 4. Okay, that's correct. Okay, so we do a similar thing to this. BA would simply mean a vector whose terminal point is A and the initial point is B, so we just have to say A minus B to get that vector, right? So what is A minus B? That is 1 minus 3, -2, and then 1 minus 5 is -4. We dot that with vector from B to C, that will be C minus B. So we say -1 minus 3, -4, and then 4 minus 5, -1. Okay, we divide that by the product of their length. So we're going to say the square root of 2 squared plus 4 squared. We've gotten that to be 20 already. And then multiply that by, this is 4 squared plus 1 squared. That will just be square root of 17, right? Great. You could say, why am I saying 4 and 1? Well, when you square negative numbers, the result is something as squaring the positive version of those numbers. So a vector from C to A would mean A minus C. That's what it would mean. So we say A, that will be 1 minus -1, that will be 2. And then 1 minus 4, that is -3. If we dot that with, well, C to B would mean B minus C. That's 3 minus -1, that will be 4. And then 5 minus 4, that will be 1, divided by their products. sorry, the product of their length. So 2 squared plus 3 squared, that will be square root of 13. Okay, because 3 squared is 9, 2 squared is 4. Then 4 squared plus 1 squared, that will be square root of 17. Good, great. Okay, so from the next page, I'll just do the following. So maybe let's just do that. Okay, so we'll take cosine of alpha to be, all right, so you come over here, we're going to compute this dot product in the numerator. I'll say negative 2 times 2, that'll be negative 4, plus 3 times 4, that'll be 12. So we say negative 4 plus 12, that's just 8. Okay, so we get 8 divided by the denominator as a square root of this times square root of that. Maybe let's just leave the math like that. So I could simply say 2 times square root of 13 times square root of 5. Maybe you can multiply square root of 13 and square root of 5 out. Okay, so we get cosine of beta to be what? Well, we just have to look at the dot product of these two. So this is negative 2 times negative 4, which is positive 8. Then we add that with negative 4 times negative 1, which is positive 4. So that will give us 12 altogether. Okay, please check that out. I'm sorry, I have to do it like this. Then this is square root of 20 times square root of 17. We do a similar thing. That will be 5 root 5 times root 17. Okay, and then lastly, cosine of theta is 2 times 4 is 8. Then negative 3 times 1 is negative 3. So that will be 5 up there. Then we divide that by square root of 13 times square root of 17. That's square root of 13 times square root of 17. Okay, great. So to get alpha, we just have to take cosine inverse or arc cosine of this. That is 8 over this denominator, which is 8 over 2 is just 4. So let me just do that. That'll be 4 over square root of 5 times square root of 13. So what is 5 times 13? That should be 65. Okay. Then for alpha, this would just mean, sorry, for beta, this would just mean that this will be cosine inverse of course, 12 over 2 is just 6. 6 divided by 5 times 17, that should be square root of 85, right? Square root of 85. And then lastly, we just get theta to be cosine inverse of 5 over that, 5 over maybe 13 times 17. Maybe you could check that out. That should be 170 plus 51. That would be 221. Hope that's correct. 221. Okay, so these are the interior angles. Maybe you could do this. Check this in your calculator. Then the next thing would be to add them up and expect to have something like 180 degrees. Okay, that was a long one. Hope you enjoyed the video. Please don't forget to subscribe to my channel, share this video with your friends. I will continue from my next video. Thanks for watching.